So how many lines can you draw through a point? Infinity, right? What about all possible circles with a given center? Again, the answer is infinity. And here's a weird one. How many non-intersecting figures of 8 can you possibly have in a plane? The size and orientation can be whatever you want, as long as it gives two externally tangent circles. Remember that there are different types of infinities in mathematics. If we introduce coordinates in our plane, we can say that every line corresponds to an angle it makes with the x-axis. And angles are described by a segment of real numbers, which, as you may know, has the same cardinality as the entire real line. This type of infinity is called uncountable because it comes after the smallest possible countable infinity. So, we have uncountably many lines here, and likewise an uncountable infinity of circles here. All I'm saying might appear trivial, since the plane itself is uncountable, and it makes sense because it is just a Cartesian product of reals with itself. Well, it did not make much sense to this fella, who pretty much explained what infinity is in rigorous terms. When Cantor established this intuition mathematically, his intuition was still rejecting. In a letter from June 29, 1877, to his colleague Dedekind, he wrote, "I see, but I don't believe it." By the way, try finding this bijection yourself. Anyway, back to figures of 8. There is no limit on their size or shape. You can even draw one inside another, and inside of that one again, ad infinitum. So, can they occupy as much space as lines or circles do? Well, that would make a terrible punchline for a video, so stop here and think. Intuitively, it feels like these figures can't produce efficient packing. Indeed, let's try proving that the best we can do is a countable infinity of 8s. Countable means that there should be a bijection with naturals. So it looks like we need to create a unique tag for every figure of 8 in any possible configuration of them in a plane. Coordinates come in handy again. Think about rational points. They have a property of being dense in a plane, which implies that inside any circle, no matter how small, we will always find at least one point with rational coordinates. So, let us find such points for every circle. Now, every figure of 8 is defined by two rational points. Now, just convince yourself that two figures can't have the same 2 points of our choice. Remember that rationals, or any finite Cartesian product of rationals, is a countable set, and our figures are tagged by a subset of such a set, so they are indeed at most countable.